predict the stock market. It feels like the ultimate challenge, doesn't it?
It really does.
The constant change, the, unpredictable events, the sheer scale of the data, and yet the promise of unlocking even a sliver of predictability, well, it holds immense potential for anyone involved in finance.
Absolutely. For decades, it felt like chasing shadows sometimes.
Right. It was all about traditional stats, economic indicators, maybe a bit of intuition,
Exactly. Bad feelings.
But now the game has fundamentally changed with the rise of machine learning and deep learning.
Oh, completely.
And that's exactly what we're digging into today, based on the source material you've shared with us, a deep dive into a research paper titled Multi-Agent Stock Prediction Systems.
That's spot on. In this paper, it really takes a serious look at how these cutting-edge AI architectures fare when you put them to the test on, well, real-world financial data.
Okay.
They specifically evaluated some of the most powerful neural network models designed for sequential data, think LSTMs, GRUs, and crucially, attention-based models.
Right, the big names.
And they ran experiments using historical Tesla stock data.
Okay, Tesla, interesting choice. So our mission here is to unpack all of that for you. What are these models really? How did the researchers set up their experiment using that specific data? And maybe most importantly, which models actually performed best and why?
Yeah, the why is key.
We want to help you cut through the technical details and understand the significant advancements happening right now in AI-driven financial forecasting, drawing directly from the material you provided.
Let's do it.
This deep dive is custom-tailored for you, built from the ground up using the sources you shared. So let's jump in.
Okay, so to give us a bit of context, the paper starts by acknowledging the history here.
Right, setting the stage.
Exactly. It points out that traditional statistical models like ARIMA or, simple linear regression tools that have been staples for years, they're increasingly being outperformed.
And the reason?
Well, the paper suggests neural network models are simply far better equipped to identify and learn the incredibly complex, nonlinear patterns embedded within financial time series data. They just capture more nuance.
And that shift is vital because, as you know, accurate stock price prediction, while difficult, is absolutely critical.
It really is.
Whether you're an investor, a trader, or a researcher, having better tools is key. And prior research cited in the paper, it consistently shows that AI and ML techniques are demonstrating significantly better performance compared to those older methods.
Yeah, it's not like a magic bullet, as you said, but it's a definite step forward. A significant one.
So who are these new players in the AI prediction game then?
So we're talking mainly about recurrent neural networks, or RNNs. They're designed specifically for data where the order matters, like a sequence of stock prices over time. It's perfect for this kind of task.
Makes sense.
Within that family, the paper focuses first on the LSTM, or long short-term memory network.
LSTM, okay. Heard a lot about those.
Yeah, and the name gives you a hint. It's built to remember information over long periods. You see, standard RNNs can sometimes suffer from forgetting earlier data points in a long sequence.
Right. The vanishing gradient problem, is that it?
That's related, yeah. LSTMs combat this using these clever internal mechanisms called gating mechanisms.
Gates, like control points.
Exactly. Think of them like smart filters or switches inside the network. There's a forget gate, an input gate, and an output gate.
Okay.
They constantly decide which pieces of historical price data are important enough to carry forward and influence the next prediction, and which information can be sort of safely ignored.
Ah, so it actively manages its memory.
Precisely. This allows LSTMs to maintain context over much longer sequences than simpler RNNs.
Got it. And then we have the GRU.
Right, the Gated Recurrent Unit.
A2.
I like to think of the GRU as maybe the streamlined version of the LSTM.
Okay, simpler.
Yeah. It also uses gating mechanisms to handle sequential data and memory, but it does it with fewer gates, just an update gate and a reset gate.
Fewer parts.
Right. And the paper points out that this simpler structure can often make GRUs faster to train. Performance-wise, they can achieve comparable results to LSTMs on many tasks.
But maybe not quite as powerful on the really complex stuff.
Potentially. LSTMs might edge them out when things get really intricate, according to some research, including hints in this paper's results later on.
Okay. LSTM, GRU. What's next?
Now, we move to a fundamentally different architecture. The transformer model. This one really shook things up in the AI world.
Ah, yes. Famously introduced in that paper, attention is all you need.
That's the one. The core difference here is that transformers don't process data sequentially, one step after another, like LSTMs and GRUs do.
Oh, How do they work then?
Instead, they rely entirely on something called attention mechanisms. And crucially, they can process the entire sequence or chunks of it in parallel.
In parallel. Okay. So how does that attention actually work in this context for stock prices?
Great question. So instead of just looking at prices one day after the next in a fixed order, the attention mechanism allows the model to dynamically look back at any point in the past data sequence. Any point it has access to, yeah. And decide how important it is right now for predicting the future price. It learns to weigh the relevance of different historical data points based on their relationship to what it's trying to predict.
Regardless of how far back they are.
Exactly.
Yeah.
Regardless of their position in the sequence. This is incredibly powerful for capturing complex, nonlinear relationships that might span, large time gaps, things an RNN might lose track of.
Got it. So it's less about remembering the whole chain of events sequentially, step by step, and more about selectively highlighting the most relevant historical moments no matter when they occurred.
You got it.
That architecture has clearly made a huge impact in other areas like language, right? Powering models like BERT and GPT that everyone hears about.
Exactly. Huge impact in NLP. And now it's being seriously applied to financial time series. But the researchers in this paper didn't stop at just testing these basic models.
Right. They went further.
They also explored enhanced versions and combined different architectural ideas to see if they could push performance even further.
Yeah, it's not just about the base model, it's how you build around it, isn't it? What sort of enhancements did they look at?
They explored several interesting ones. One was the two-path architecture.
Two paths? Like parallel processing again?
Sort of. As the name suggests, it processes the input data through two separate streams, two separate internal pathways.
Okay.
The intuition here, the idea, is that these two paths might be trained to capture different aspects or scales of the data. Perhaps one path focuses on very short-term fluctuations, while the other takes a wider view to capture longer-term trends, trying to get the best of both worlds.
It's interesting. What else?
Another is C2-sec, which is short for sequence to sequence.
C2-sequer, I heard that term too.
Yeah, it's an encoder-decoder structure. Basically, an encoder part reads the input sequence, say, the last month of stock prices, and distills its essence into a kind of summary, a context vector.
Okay, compresses the info.
Right. And then a decoder part takes that summary and generates an output sequence. This is particularly useful if you want to predict not just the next single price, but maybe the sequence of prices for the next week or month.
Ah, predicting multiple steps ahead.
Exactly. Variable length inputs and outputs.
And the bidirectional models. That sounds intriguing. Processing in two directions.
It is pretty cool. Instead of just processing the sequence from past to present, like reading a sentence left to right, a bidirectional model processes it in both the forward and reverse direction simultaneously.
So it looks ahead. Well, ahead within its window.
Within the context window it's examining, yes.
Yeah.
By looking both forwards and backwards, the model can potentially build a richer understanding of the relationships between data points. It uses context from what came before and what came after within that specific input sequence it's looking at.
So it's like getting a more complete picture before making a decision on the next step.
That's a good way to put it. More context.
And the paper even looked at combining these ideas, stacking them.
Absolutely. They tested models like, for instance, an LSTM that was both bidirectional and used a C-cosec structure, layering these capabilities to see which combinations yielded the best results.
Okay, so a lot of different variations on the table.
Definitely. Now, to really see how these different architectures stacked up, the researchers needed a battlefield, so to speak.
The testing ground.
Exactly. And they chose historical data for Tesla stock.
Okay, so Tesla was the test case. What kind of data points?
They used the standard financial data points you'd expect. Date, the open, high, low, and close prices.
The OHLC.
Right. Plus the adjusted close price and the trading volume. As the paper notes, the close price is often a primary target for prediction because, it's widely used in trend analysis.
Makes sense. And how did they set up the actual test?
So they set up the experiment in a way that simulates how you'd actually try to predict the future. Pretty standard practice.
Train on the past, test on the near future.
Exactly. They trained all the models on the Tesla data up to a certain point, specifically 30 days before the end of their data set.
Okay.
And then they tested how well each model could predict the prices in that final unseen 30-day period. It's a classic way to measure forecasting performance. See how well it generalizes.
Right. You can't peek at the answer.
Precisely. They also ensured the testing environment was consistent and rigorous. specifying details about model configurations like layers, hidden units, learning rates, and the tools used like Python and GPUs on Google Colab to make sure the comparisons were fair.
Good, good. Rigor is important. Okay, let's unpack this. After all that training and testing on Tesla data, who came out on top? This is where it gets really interesting.
Yeah, the results table in the paper is pretty compelling. The clear overall leader was the attention model.
The transformer-based one.
That's the one. It achieved the highest accuracy score by a noticeable margin, hitting 95.1467%.
Wow, over 95%. That's high for stock prediction.
It is quite high, yeah.
Yeah.
Now, if we look at the foundational RNNs, the standard LSTM performed better than the standard GRU.
As suspected, maybe.
Perhaps.
Yeah.
LSTM was at 89.2522% accuracy compared to GRU at 84.1694%. So clear edge for the baseline LSTM there.
Okay. And what about those enhancements? Did they help?
Adding those architectural variants had a significant impact on the LSTM's performance.
How significant?
Well, the LSTM2 path jumped up to 94.1620% accuracy.
Big jump.
Huge jump. And interestingly, the LSTM bidirectional matched that exactly, also hitting 94.1620%.
Same score. Interesting.
Yeah. The standard LSTM Seek-to-Sake, though, surprisingly didn't move the needle much on the baseline LSTM, staying around 88.3902%.
Oh, okay.
But the true powerhouse among the LSTMs was the combined LSTM bidirectional Seek-to-Sake. That one achieved a very high 95.0921%.
Whoa, almost catching the attention model.
Extremely close, just fractions of a percent behind.
Okay, what about the GRU side? Did the variance help there?
It was a bit more mixed for GRU. The two-path version actually saw a slight dip in accuracy compared to the baseline GRU.
Oh, didn't work there.
Not in this test, no. But the GRU bidirectional showed improvement over the base GRU, reaching 87.0331%.
Okay, bidirectionality helped GRU too.
It did. And the GRU C2-Sec saw the biggest jump for the GRU family, hitting 90.8855%.
So C2SIC was good for GRU, but maybe less so for baseline LSTM.
That seems to be the case here, yes. And finally, the GRU bidirectional C2-Sec landed at 87.3672%, slightly better than the bidirectional only GRU, but not as good as the C2-Sec GRU on its own.
Okay, so pulling all that together, we see a hierarchy emerge, right?
Yeah, right.
The pure attention model was the best performer,
Yep.
followed extremely closely by that top-tier combined LSTM variant, the bidirectional CQ-Sec one.
Neck and neck, almost.
Then you have the other strong LSTM variants and the better GRU variants, especially the C2-Sec version for GRU. And finally, the baseline LSTMs and GRUs kind of bringing up the rear, relatively speaking.
That summarizes it perfectly.
So the paper digs into why, right? Why these differences in performance.
It does. It offers some valuable analysis trying to understand the strengths of each architecture based on these results.
What did they find? LSTM versus GRU first.
So comparing the baseline LSTM and GRU, the findings suggest that LSTM's more elaborate gating system, those separate forget input and output gates we talked about,
Yeah.
it seems better equipped to capture and maintain the really critical information within the complex, long sequences of stock data. It gives it an edge in this specific, quite challenging task over the slightly simpler GRU gates. More fine-grained control, maybe.
Okay, so the complexity of LSTM paid off here. What about bidirectionality?
The benefit of bidirectionality was pretty consistent across both LSTM and GRU. It helped both.
Right, we saw that in the numbers.
As you suggested earlier, processing the data in both directions clearly provides a more complete picture. It just enriches the model's understanding of context within the sequence it's examining at any given moment.
Makes intuitive sense. And Sexusake, that was more mixed.
It was. It significantly boosted the performance of the GRU model, suggesting the encoding-decoding structure is particularly beneficial there, maybe helping it structure the information better.
Ah.
For the baseline LSTM, it wasn't a big help on its own. But crucially, it was a key component in the highest performing LSTM variant, that bidirectional Sec-to-Sec model.
Right.
So this indicates Sec-Sec's effectiveness might depend on how it's combined with other architectural features, or maybe which base model it's paired with.
Interesting synergy effects.
Exactly. And then there's the dominance of attention. Why did it win, or almost win?
Yeah, what's the secret sauce there?
Well, the paper's analysis points back to its fundamental difference. It doesn't get bogged down in that strict sequential processing.
Right, the parallel aspect and looking anywhere.
Precisely. By using attention, it can directly and dynamically identify and weigh the most important past data points, regardless of how far back they are. This ability to just focus on the critical moments in the time series, it's incredibly powerful for capturing those complex, nonlinear relationships that traditional sequential models might struggle to fully retain over long stretches of time. It cuts through the noise better, perhaps.
Wow. Okay. That 95% accuracy number, roughly, for both attention and that top LSTM variant is really striking.
It really is.
It underscores the power of these more advanced architectures.
Hmm.
So when we think about this from your perspective, the listener's perspective, why does understanding these models and their performance on something like Tesla stock actually matter? What's the takeaway?
Well, this deep dive, drawing directly from the research you explored, it really shows us just how quickly the frontier of AI in financial forecasting is moving.
Things are changing fast.
Very fast. These sophisticated models, especially those leveraging attention or these powerful combinations like bidirectional sec-to-sec LSTMs, they aren't crystal balls, right? They don't give perfect predictions.
Of course not.
But the numbers here show they offer significant leaps in accuracy and potentially efficiency compared to older methods, and even compared to the simpler baseline RNNs.
A clear improvement.
A clear improvement. Understanding which models are performing best, and critically, why, like the power of attention or bidirectionality, gives you key insight into the technology that's driving modern quantitative finance and AI-powered trading strategies today.
So it helps you understand what the pros are using or researching.
Exactly. It highlights that the focus is shifting towards models that can dynamically identify the most relevant data points and patterns, rather than just processing data rigidly in sequence. It helps you see the potential these tools have for maybe deciphering some of the complex temporal dynamics of markets a bit better.
Okay, so the main takeaway here seems pretty clear. While LSTMs and GRUs are solid workhorses for sequential data,
Definitely still relevant.
architectures that can selectively attend to the most relevant information, like transformers, or combine powerful features like bidirectionality and sequence generation in LSTMs, are pushing the boundaries. They're achieving higher prediction accuracy based on this specific research.
Yeah, they're proving more effective, in this study at least, at decoding those complex market patterns found in the Tesla data.
Which leads us to a final provocative thought for you to consider, something drawn from the paper's look at future directions.
Ah, where things might go next.
Exactly. The research mentions exploring hybrid models, models that combine attention with other advanced techniques, or perhaps integrating them with different types of data. The literature review even touched on incorporating things like, say, sentiment analysis from news or social media.
Right, bringing in external factors.
So, the thought is this. How might combining these already powerful architectures like attention or these advanced LSTMs with even more diverse and non-traditional data sources? How might that fundamentally change AI's ability to understand and maybe even predict complex systems like the stock market?
That's the million-dollar question, isn't it?
What possibilities does that open up? Something to think about.